Come on. You can do it. So I'll be sending out an email about it later because I forgot to put the one thing up originally. But so chapter 3 is a tiny bit different. The notes will look a bit different. That's just essentially because what chapter 3 is we're just going to now find a bunch of these rules and kind of these processes for finding the actual derivative function. So up to this point, we've only been able to estimate the derivative value at a certain point using that instantaneous rate of change with the average rate of change. But now we're actually going to be able to find the full function that we're going to be able to use. And for your homework, it's kind of going to come in 2 pieces because if you look at the Wiley, that should be up now. But anyway, the Wiley for this week is shorter than usual. It's like 9 questions instead of like 20 or 30. And that's because if you thought Wiley was bad before, oh buddy. Wiley for chapter 3, the large majority of chapter 3 is absolutely horrendous. I will put in the correct answers in as many formats as I think I can, and it still doesn't accept it. So essentially, the only thing that I put on Wiley are some very specific types of questions that don't have that issue. It's going to seem very similar to stuff from chapter 2. So the Wiley homework is going to feel disjointed in a way, but it's technically not. It's just doing the same types of things from 2.2, not 2.2, just chapter 2 in general, interpreting. I don't think there's any tangent lines on there, but you're going to be finding derivative values, but you're going to be using the functions to do so. You're going to be interpreting things, so it's going to be very similar to the stuff you did in chapter 2. It's just now we have these this way to find these derivative functions exactly. And then what I'm going to do also, and again, I'm going to be sending out a big email about this later, is that on Blackboard, I'm going to put up a kind of worksheet of kind of things that look more like this, just these derivative problems. And while you should do it, as much of it as you need to feel confident, I'm not going to try to check that in any way. I don't know how I'd be able to collect that from everyone when some people don't come to class in person, some people do, all that jazz. So there will be the Wiley homework, which again is short. And then there's going to be this worksheet up on Blackboard that you should attempt as much of as you need to feel comfortable. And the answers will be up. You'll be able to check your answers. The work will be there. You'll be able to look it over. But that's kind of more of a just honesty thing. You do it until you're comfortable. And that's just how it goes. So anyway, I'll send an email about that later. If you have questions, just email me and I'll answer them. So derivative rules. So with these, I'm going to kind of give you some background for like these first 2. But after that, it's kind of a trust and believe me type of deal. And it's just like, you might not know why these rules hold, but they do. Trying to prove the fact that they do hold, especially when we get to some of the later rules, is very complicated and very in-depth and way past the scope of our class. But just know that you get to use them just freely. You will need to memorize them. But essentially, you should be using them so much that memorizing them should hopefully not be that hard after a little bit of practice. But anyway, so let's get started. So say, let me reshare my screen just in case. Boink. There we go. Now I'm going to write all these rules in terms of Leibniz notation, just because writing them out is easier in Leibniz notation. So say I want to take the derivative. So that's all this notation means, this d over dx, it just means take the derivative. So say I want to take the derivative of a constant, of a number that doesn't have a variable attached to it. The derivative of a constant is going to be 0. I can give you a little bit of an explanation on that. So if you think about it, remember that the derivative is a slope. I've said that about 5 times, and you really need to get it in your brain. Derivative is a slope. So say I have a constant function, so it's just a straight horizontal line. What's the slope of that function? Well, the slope of that linear, kind of straight horizontal line is 0. So that's kind of why the derivative of a constant is 0. Say we have the derivative of a linear function. Now I'm going to have this linear function not have a y-intercept. Well, shall I say a y-intercept is 0? So it's just going to be some mx instead of mx plus b. I'll talk about the mx plus b form in a second. But if you have that, well, then you just have some, some straight line that goes through the origin. And, it's got the equation mx. So what's the slope of that line? It's just whatever n is. So the derivative of some constant times x is just going to be that constant. And now we get to the ones where you kind of just have to trust and believe me. If you have the derivative, if you want to take the derivative, I should say, of essentially two functions that are added or subtracted. So that's kind of what I'm doing in the middle. They could be added or they could be subtracted. What you do is you take the derivative of the first function and you add or subtract it, depending on which one you started with, to the derivative of the second function. So essentially, the nice thing about derivatives is we can just kind of jump through addition and subtraction. We just kind of take the derivative of each piece and then just kind of plop it together. And then the derivative of a constant times a function. So let me use C. A lot of times you'll see this presented as K times f of x. But then someone in my last class was wondering why I used C for a constant in one case and K in the constant for another case. It really doesn't matter what constant I use, but I'll just try to be consistent. Oops. So essentially what happens here is the constant, I like to say, comes along for the ride. Just kind of sticks out front, and then you just take the derivative of the function separately. Catch up to me, screen. There we go. I guess I'll do this right now before I go to these examples. So if we wanted to take, so I talked about a linear function with no y-intercept, but what if we had some y equals mx plus b? Well, if you think about in general, what is the slope of that line? It's still, excuse you, screen, it's still just m. This here is technically a combination of those two rules. So like it doesn't need its own separate rule, but I'll just write it down there just because. Actually, kind of a combination of these three rules, because you would need the derivative of b, which would just be 0. But anyway, so it's kind of a combination of those three rules together. Oh, I should write this down. I'll write it in a different color. A special case of the mx case is that the derivative of just x is 1. It's technically covered under that case, but for some reason a lot of people don't realize it, I guess. And then they forget what the derivative of x is. So the derivative of x just by itself is just 1. So let's look at some examples. Excuse me. So I'm gonna go through the first row, and then I'm gonna have you try the second one. I'm gonna kind of pause after each one to kind of give you some time to not only catch up to me, but also ask questions if you have them. Because obviously I can't see your faces and I'm just talking at a screen. Please feel free to stop me at any time in chat or unmute yourself, or else I just will keep going. With these, they build upon themselves very quickly. So if you're not understanding some of the more basic ones, you need to ask before we get to the harder ones. We'll ask whenever you need to, even if you're a little too late to the game. But just ask, please. This is definitely not something that you want to wait a while to try to ask about if you're confused. But anyway, so let's try to differentiate these functions, so essentially find the derivative. So if I want to find the derivative of the function that's just equal to 175, 175 is just a number. There's no x there. There's no variable anywhere. It's just a number and a number by itself. So it's a constant. So the derivative of a constant. Oh my goodness. Zoom back out. Stop this. Why do you do this to me? So the derivative of a constant is 0. Oh, let me scroll back up. Get that roll in there. Hello. Here we go. So the derivative of a constant is 0, so the derivative of 175 is 0. And then again, I'm going to do the first row, so I'm kind of going to go over to number 3. So now I have 19x, so something times x, and mx. So the derivative of that is just 19, because now we have that variable, so it kind of changes the rule that we're working with. So the derivative of 19x is just 19. And then popping over to number 5. The derivative of this, now we're looking in terms of t. Well, now we kind of have to bring in that sum or difference. So we need to take the derivative of 2 first. So what's the derivative of 2? It's a number by itself, no variable. Derivative of a constant is 0. And then I have to add that to the derivative of 6t. So we have a constant times t. So it's going to essentially be our second rule. So that's just going to leave us with 6. So of course the final answer is 6. Now, once you start getting good at these and you've done so many of them, I'm going to be writing out a lot of intermediate steps, especially for the ones we're about to do for the thing called the power rule. You don't have to write out those intermediate steps. Intermediate, sure, why not? Steps if you don't want to.
Can you explain number 5 again?
Yeah, give me 1 second. So you don't really need to write out those intermediate steps if you start getting really good at these and just want to jump straight to the answer and you know how it works. That's perfectly fine. So 5, we have a sum of things. So that means we are going to want to look at this derivative of sum or difference rule first. So that tells us that we essentially take the derivative of each piece separately. So now what we need to do is we need to look at, let me just erase the whole thing. So what's the derivative of 2? Notice there's no variable attached to that number. It's just 2. There's no t anywhere. So since it's a number completely by itself, so we're in this case up here. So the derivative of a constant, oh my goodness, I really don't know why it does that, is 0. So the derivative of 2 gives us 0. And then I have to add that to the derivative of 6t, because that's what my sum and difference rule tells me. I have to essentially take the derivative of both pieces and then just add them together. What's the derivative of 6t? Well, there's a t in there, there's a variable. So we're essentially in this case right here. I know it has an x in the rule, but it can be whatever variable you need it to be. So since it's 6 times t, the derivative of that is just that number 6. And then of course 0 plus 6 is 6. So the actual full answer would just be 6. Does that make sense?
Yes, ma'am.
Hooray. All right, I'm going to sit awkwardly in silence for the next minute while you guys try 2, 4, and 6. 6 is the tiniest bit tricky if you don't realize what's going on, but I'm going to awkwardly sit for a minute while you do that. Just a few more seconds. These ones should hopefully be semi-quick. I know it might be some of your first looks at these types of things ever, but. For number 2, -2 is just a constant. It's a number by itself. There's no variable attached to it at all. The derivative of a constant is 0. Catch up to me, screen. One of my screens is caught up, the other one is not. Come on, buddy. There we go. For number 4, the derivative of -27t. That's just a number times the variable. So we're kind of in that second case for the linear function, so it'll be just -27. Now this last one might have tripped up some of you. derivative of 25x, so we have to take the derivative of each piece and add them together. So the derivative of 25x is just 25. The derivative of pi is a number. There's no variable attached to it, so its derivative is 0 because pi is a constant. So the answer there is just 25. Questions, concerns on any of those before we go on to our next rule, which steps it up a tiny bit?
No.
Okay. All right. Kind of leave that last line up there. So we've got the power rule now, and that's going to tell us the derivative of some x to the n. So I'm going to write over here variable to a number. That's going to come up. The reason I write that down is going to come up on the next page, but anyway. So essentially what you do here is you're going to bring the power out front, and then you're going to subtract 1 from the power. So you'll hear me say something a lot like bring the power down. Subtract 1 from the power. Now again, I'm going to be doing a lot of intermediate steps here, especially for those people who might not have seen derivatives before in their life. If you don't need to do them, don't do them. You can just jump straight to the answer if you know how this goes. I taught high school a few years ago, and they decided to call this one the yeet it and drop it. So if that helps you in any way for some reason, go ahead and refer to that. But anyway, it's the power rule. So say I want to find the following derivatives. Let me split this up so that I don't accidentally run into my next problem. Oh, I need to do a side note first. Side note. There are two exponent rules that you really need to know pretty well for the power rule. The first one is if you have essentially a root, and even if you have a power inside of that root, this is going to be equivalent to x to the m over n. So specifically, if you just have a root, it's going to be 1 over that root number. And then also if you have 1 over x to the n, that is equal to x to the negative n. Now those have nothing to do with derivatives. Those are just generic exponent rules, but they do come into play a lot with these power rule questions because sometimes you have to rewrite the original question before you can take the derivative. All right. So let's look at a couple of these. So say I want to find the derivative of x to the 8th. So what we're going to do is we're going to bring that power out front, subtract 1 from the power. Wow, that one's lagging a lot. Let me try to reshare just in case that helps. No, that one's lagging. This is so stupid. So our answer here would be 8x to the 7th. Again, if you don't have to write out this intermediate step of actually showing the subtraction on the exponent if you don't need to. And so again here, stop me whenever you need to. I'm just going to kind of pause for a second after each one and then keep going if no one stops me. So on this next one, we kind of have to rewrite this first because it's not in the right format. We don't have x to a power, we have 1 over x to the power. So we use that exponent rule that I just reminded us of to rewrite this as x to the negative 3rd. I have not taken a derivative yet. For some reason, lots of people think the rewriting step is the derivative. It is not. All I've done is rewritten the original question so that now I can take its derivative. So bring the power out front, subtract 1 from the power. So negative 3 x to the negative 4. If you want to rewrite this as negative 3 x to the positive 4th, that's perfectly fine. You don't need to. You can totally leave it as negative 3x to the negative 4th. That's perfectly fine. Whatever floats your boat. And so number 3, we also have to rewrite first has nothing to do with taking the derivative, but we should rewrite that as x to the 1/2. Once I rewrite it, I can take its derivative. Bring the power out. Subtract 1 from the power. So 1/2 x to the negative 1/2. Again, you could rewrite that without the negative exponent, but I don't want to scroll down and get rid of the rule, so I'm just going to leave it like that. For number 4, we have the tiniest difference here, and that's the fact that we now have this 2 in the front. We didn't have constants in the front for the first 3. So we have a constant in the front here. So what we're going to do there is the constant just kind of comes along for the ride. So it just kind of tags along. And then we have to multiply by the derivative of this x to the 4.5. So for that derivative, we bring the power down, subtract 1 from the power. Two times 4.5 is 9, x to the 3.5. Once again, if you can jump straight to the answer, go right ahead. Once you've done enough of these power rule ones, you usually get pretty used to them. For the 5th one, this is an unnecessary step, but I'm going to take it anyway. I'm going to rewrite this as 1/4 times x squared, same thing. So if I want to take the derivative here, that 1/4 in the front of the x squared comes along for the ride. Then I have to multiply by the derivative of x squared, which is 2x, and subtract 1 from the power. And then I have to add, oh my goodness, the derivative of 3. Zoom back out. 2. So I have to add on the derivative of 3. Derivative of 3, there's no variable in there. It's just a constant completely by itself. The derivative of a constant, 0. 1/4 times 2 is 1/2. X to the first, oh, plus 0. You don't have to write that. So just 1/2 x. I want you guys to try 6 and 7. I'll give you a minute and a half. And then we'll go over 7 and 8 together. All right. Derivative of 6, -3 comes along for the ride. Bring the power down, subtract 1 from the power. So you'll get 12x to the -5th. Number 7 is one of the longer ones we've seen, but it's just the same rule, just because of the fact that we can essentially move through that addition, we just take the derivative of each piece separately. So bring the power down, subtract 1 from the power. 2 comes along for the ride, bring down the power, subtract 1 from the power. derivative of 5x, since it's just 5 times a single occurrence of the variable x, that's just going to be 5. And then the derivative of 4, which is a constant completely by itself, is going to be 0. So we'll have 4x cubed plus 6x squared plus 5. Should also make a side note really quick. So before, we had the derivative of this above some mx. This is technically a power rule because we'd essentially bring the constant out front and then take the derivative of x to the first, which would be bring the power down, subtract 1 from the power. Whoops, I got ahead of myself. Which would be mx to the 0, but anything to the 0th power is just 1, so that's why that's kind of how that holds. So if you want to think about the derivative of something times x as a power rule, you totally can. It'll work out. I personally just find it easier to think about it as its own completely separate rule, but whatever floats your boat, whatever is easier for you, it technically is a power rule if you want to view it as one. So for number 8, the first thing we should do is rewrite this as x to the 1/3 plus x to the -2 minus 5x. Again, that's just rewriting it. I have done nothing to take. So to take its derivative, bring the power down, subtract 1 from the power. Add that to the derivative of x to the -2, bring the power down, subtract 1 from the power. Subtract the derivative of 5x, which is just 5. Simplify it down a tiny little bit. 1/3 x to the -2/3 minus 2x to the -3rd minus 5. And then number 9, we have x to the pi. Pi is just a number, so this holds. So bring the power down, subtract 1 from the power. And you kind of got to leave it as pi minus 1. Questions, concerns about power rule before we move on to some more rules? Hold on for like 15 seconds. Because I know typing things in chat can take a little bit. Seems like we're good. Okie dokie. Moving on then. Again, please don't be scared to stop me. Yes, I can. Let me just erase all this. Blink, 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 blink. To use the power rule, I need something that looks like x to the n. I don't have that for the first 2 terms yet, so I should rewrite that using our exponential rules. So the cube root of x can be written as x to the 1/3. And then 1 over x squared can be rewritten as x to the -2. And then the minus 5x is just minus 5x. So I kind of need to do that first before I go about taking the derivative. And now that I do that, let me just kind of write down our power rule over here so I can refer to it. So our power rule says essentially bring the power down into the front and then subtract 1 from it. So if I have x to the 1/3, I'm going to bring that 1/3 out to the front. I'm going to take 1/3 and I'm going to subtract 1 from it. And then I'm going to add that to the derivative of x to the -2. So since -2 is my exponent, I'm going to bring that exponent down. And then I'm going to subtract 1 from it. And then I need to subtract the derivative of 5x. Now that's technically a power rule if you want to treat it as such, but we also have the rule that we started with that said the derivative of something times x is just essentially that something. So the derivative of 5x would just be 5. The derivative of kx would be k. The derivative of 99x would be 99. And then the last thing we can do is just rewrite it. So 1/3 minus 1 gets us negative 2/3. I can write the plus negative 2 as just a minus, x to the negative third minus 5. Did that help? Cool. So yeah, sometimes with these we need kind of to do 2 steps. We need to rewrite the original in terms of some different exponents if necessary, and then take the derivative. All right, I'm not seeing any more questions, so I will move on. So our next set of rules. So the derivative of a to the x. Now notice in the one beforehand I had written variable to a number. This is number to a variable. Very different, completely different rules. So if we want to take the derivative of some a to the x, this is equal to the natural log of a to the x. This is the grossest rule we have, in my opinion. More importantly, is we have a very special case of this rule where it's the derivative of e to the x, because remember, e is a number. I, and almost no mathematician, will ever use e as a variable. Whenever you see an e, you can very highly assume it's a number. So the derivative of e to the x is e to the x. If you think about it, the natural log of e is 1, so that kind of piece goes away. Now we're going to use this a to the x rule in the ones below. When it comes to a quiz or an exam, I can pretty much guarantee that I will 99% sure not use a regular a to the x. It will always be an e to the x. Because those ones, the e to the x rule comes up much more often in contextual problems and actual applications and such. But anyway, if we want to take the derivative of some e to the kx for some constant k, now this is technically what's called a chain rule. We haven't talked about chain rule yet, so some of you might not know what that is. I don't know why your book presents this as a completely, honestly do not. But I do it just to keep in line with what your book does. It's technically a chain rule. I'm going to stress that again about 5 more times once we actually get to the chain rule. But we can take care of these because it's kind of a simple occurrence of the chain rule. You essentially bring that constant out front, but then essentially rewrite the whole entire e to the kx. And then if we want to take the derivative of the natural log of x, this one's the one that changes the format the most. Most of them kind of have a similar format. This one just kind of throws that out the window because the derivative of the natural log of x is 1 over x. So we've got 15 minutes. So we should be able to do as many of these as I did in my last class, which is good. All right. So I'll give you like 5 more seconds to write those down. And now let's go through some examples. So let me try to scroll down the tiniest bit. That's not right. There we go. So find the derivative. So we start with 2 times 3 to the x plus 5e to the x. Let me split this up so I don't run into my next problem. And let me start over here so I don't run out of space. So if I want to take the derivative of this, so I have 2 times 3 to the x. Please, for the love of all that is good and holy, that is not equal to 6 to the x. You cannot combine together that 2 and that 3 to the x. So essentially what needs to happen is that 2 is going to just come along for the ride. And then I need to take the derivative of 3 to the x. If I go back up to my rule, what's the derivative of 3 to the x? That would be the natural log of 3 times 3 to the x. Then I have to add that to the derivative of 5e to the x. That 5 comes along for the ride. What's the derivative of e to the x? E to the x. You can't really rewrite that anymore. If you wanted to type in 2 times natural log of 3 into your calculator and get a decimal, I guess you could, but I would just say leave it. And you don't really need those multiplication dots in between them, but I just think it breaks it up kind of nicely. Number 2. If I want to take the derivative here, what's the derivative of e to the x? It's e to the x. Need to add that to the derivative of 2 to the x. So my a to the x rule tells me that that's natural log of 2 times 2 to the x. And then I have to add that to the derivative of 7. There's no variable in that. It's just a 7. So the derivative of a constant is 0. You could rewrite that slightly if you want to. Now, unfortunately, I have to scroll down past these rules to get to the next one. But hopefully you have them on some paper in front of you so you can look back at them. So number 3, let me bring this down. Okay. So if I want the derivative here, I have 8x squared. If I want to do that very generically, that 8 comes along for the ride. And then for the derivative of x squared, bring the power down. Subtract 1 from the power. Plus the derivative of 8 times e to the x. The 8 kind of comes along for the ride. Times the derivative of e to the x, which is just e to the x. Plus the derivative of 8 times 4 to the x. So that 8 comes along for the ride. Derivative of 4 to the x is natural log of 4 times 4 to the x. It's not much to simplify here, but we could do 16x to the first. 8e to the x plus 8 natural log of 4 to the x. I'll pause really quickly before moving on because I'm going to skip down to the next problem and do the first column of that problem as well. That's probably where we're going to end for the day. If we get to some more, we'll get to some more, but then we'll tackle them on Wednesday. 5 more seconds in case there's questions. All right. So let's do some that have some natural logs in it. So let me try to leave that last one in there. There we go. So again, I'm going to skip down to this first column of the second problem. So once again, just finding derivatives. That's essentially all we're doing this week. It's just finding derivatives until our arms fall off. So I want to take the derivative of t. The 5 comes along for the ride. And then I have to take the derivative of the natural log of t. Our rule tells me that this is just 1 over t. I add that to the derivative of 7e to the t. That 7 comes along for the ride. Derivative of e to the t is e to the t. Subtract the derivative of 4x squared. 4 comes along for the ride. Bring the power down. Oops. Subtract 1 from the power. And again, if you get good at these and can start skipping these intermediate steps, go right ahead. Derivative of 12, there's no variable in that, it's just a constant, so the derivative of a constant is 0. If you want to, you can rewrite this as 5 over t, or you can leave it as 5 times 1 over t, whatever floats your boat. Come on, pen. 4 times 2 is 8, t to the first, and we don't really need to rewrite the minus 0. All right. Next one. We've got the derivative of 1/6. Oh my goodness. The derivative of 160. 160 is a number completely by itself. There's no variable attached to it, so the derivative of a constant is 0. Plus the derivative of 3t squared. 3 comes along for the ride. Do your power rule. Bring the power down, subtract 1 from the power. Oh, goodness. Minus the derivative of 2t, which is just going to be 2. Plus the derivative of 2 times the natural log of t. 2 comes along for the ride. Derivative of natural log of t is 1 over t. And we can rewrite that a little bit if we want to. In general, you never really have to rewrite them if you just want to write them out. Like if you wrote this on an exam or a quiz, it would be perfectly acceptable. Triple check my instructions, see if it says simplify, but I rarely ever ask you to simplify. Though in chapter 4, we're going to be using these derivatives to do something else, so you kind of need them in a more simplified way. So you also kind of want to get used to simplifying them at least a little bit. All right. Number 3. This one has a slight trick to it, and nudge, nudge, wink, wink, it's a trick that I like to pull a lot. Notice 4e to the third. There's no variable in that. Remember, e is not a variable, it's a number. So it's a number times a number to a number. So this is just a number. Like there's no variable in there at all. So that's a constant. So the derivative of 4e cubed is 0. And then I have to take the derivative of 2.45 natural log of t. So we have 2.45 that kind of comes along for the ride. And then the derivative of the natural log of t is just 1 over t. So if you like, you can rewrite that. Or you can leave it, whatever floats your boat. Questions, concerns on any of those? I will keep going a little bit because we've got a bit more time. Maybe like 10 seconds. Yeah. Look at that, Carson, and notice there is no variable there at all. I have 4e to the third. E is a number, always and forever. It's never going to be a variable. So since that's essentially a number times a number to a number, there's no variable in that. There's no t, there's no x. It would have had to be a t in here because it's f of t. But since there's no variable in there, it's just a number. Like if you type that into your calculator, what actually is that? If I type 4e to the third into my calculator, 4e to the third, I get 80.34 blah, 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 blah. So if you were to rewrite it like that, if I were to take that 4e to the third and rewrite it as 80.34, what's the derivative of 80.34? Well, that's just a number, no variable. So a derivative of a constant is 0. So that's why that becomes 0, is because that thing is just a number. And again, this is a trick that I do like to pull a lot. Nudge, nudge, wink, wink. Giving you something that has an e in it and almost looks like you need to take the further derivative of it, but it turns out to just be a constant. So that's that. Hopefully that made sense. It's just a number. All right, 5 minutes. So let me scroll back up to this other set and do a couple more of those. Especially because we haven't done any with the e to the kt, so let's go ahead and do a couple of those, I guess. Let me zoom in on that. You know what? No, never mind. I won't. Let me try to scroll up and get these rules back in here. That one at least. All right, let's see. So if we look at number 4 up here, and I want to take the derivative. First thing I need is the derivative of 5. That's just a number by itself, no variable there. So that's just a constant. Derivative of a constant is 0. Plus the derivative of 3x squared. 3 comes along for the ride, bring the power down, subtract 1 from the power. Minus the derivative of e to the negative 0.2x. So here, 7 comes along for the ride. And we have this e to the k rule we have up here, which tells us that we essentially bring that constant out front and then essentially rewrite the entire e to the kx. We can simplify that a little bit if we wish. Negative 7 times negative 0.2 is positive 1.4. So there's our derivative for that one. Number 5. e to the 1/3 x. There's an x in there, so we need to use our e to the kx rule. So the 15 comes along for the ride. And then our e to the kx rule says bring the 1/3 out front. And then essentially rewrite the entire e to the kx. Minus the derivative of 17x, which is just 17. Again, that's technically a power rule if you want to treat it as such. But again, it's also kind of that rule we presented at the very beginning. Clean that up. So you could, of course, simplify this. 15 divided by 3 would be 5. So 5 e to the 1/3 x minus 17. And then we'll just finish on this last one. Probably be like a minute early, but that's all right. So say I want to take the derivative of this. That 2 comes along for the ride. Let's take the derivative of e to the negative 1.9x. My e to the kx rule says bring that constant out front and rewrite the e to the kx. Minus the derivative of 14. There's no variable there. It's just 14 by itself. Derivative of a constant is 0. 2 times negative 1.9, negative 3.8 e to the negative 1.9x. And you don't have to rewrite the minus 0. Come on, screen. Catch up to me. It'll catch up eventually. There we go. All right. So we'll just end with that one. We'll start those next 3 from the other one. Will probably just end up being your warm-up on Wednesday. Your quiz, I haven't completely decided yet. Well, it's going to be derivative rules. I should just say that. Essentially, anything we've done today is fair game. So where we were originally started with, where it's just, some power rules. But then we can also use these rules as well. And of course, I can start asking you questions like the number 4 that we just did. That combines a bunch of the rules together. You've got the constant rule, you've got the power rule, you've got the e to the kx rule. So your quiz will be on derivative rules that we've gone over today. Nothing that we go over on Wednesday will be on there because we're going to move on to the chain rule on Wednesday. No, it's just going to be these rules. So essentially stuff we did today, and that's going to be it. Because these rules are that important that I just want to focus on just these types of rules. So anything you saw today is fair game. Otherwise, well, I don't know what to say, but otherwise. Again, I'll be sending out an email about that kind of weird homework that we have going on this week. You do have Wiley. It's just not going to be as long as normal. And then there will be kind of a separate side thing that you kind of do on your own at your own pace that'll be essentially like this. You just have a ton of derivatives. You get to do as many or as little of them as you find you need to do to be able to feel confident. So I'll be sending out an email about that later. Otherwise, we're done. If you have some questions, feel free to stick around. Otherwise, have a great day. I'll see you on Wednesday. Yeah, I'm going to stop recording it.